Hello everyone, this is Engineer Selassie from Melo Academy Brain Boosters. We are chapter 5. We get a lot. We came a lot. So this is address translation, a very nice chapter. So let's get into it. So memory virtualizing with efficiency and control. Memory virtualizing tasks, a similar strategy known as limited direct execution. This one we have seen how memory was virtualized for efficiency and control. So this is how the operating system gain its access, yes, limited direct execution. In memory virtualizing, efficiency and control attained by hardware support. And example, we need registers, we need translation Lookaside buffers. These are the buffers which all the virtual memory translated into the physical memory. All the information will be found in the TLB, the page table, and everything. Also provided flexibility, allow process to be able to use their address space in whatever way they like. So address translation. What is address translation? Hardware transforms a virtual address to a physical address. So we have physical address and we have virtual address. The desired information is actually stored in the physical address because every code, anything is found in the physical address. But the operating system creates a fantasy for the running process that each process has its own memory address space. That is a virtual address. Whatever code you write, whatever you see in your computer, whatever we have seen in chapter 13, all the code, the address we see is virtual addresses. So this virtual address should be transferred to physical addresses. The operating system must get involved at key points to set up the hardware. The operating system must manage memory to judiciously intervene. So current assumptions, we have three assumptions. The first one is user's address space is placed contiguously in physical memory. So the user address itself is inside the physical memory. The address space size is not too big, less than the size of the physical memory, because we have physical memory and we have address space. So the address space is smaller than the physical memory. Address space size for all processes are the same. Now the pages are all the same. These are the assumptions, but we will relax it later. Let's see this simple code, address translation, how it does this simple code. As you can see, this is C language, void function. So we have int x 3000. And what it does is x is equal to x plus 3. It will add 3 and it will store it in the same memory location. So this is the line of code we are interested in. But what it does first load a value from memory, because this int x is 3000 is in the memory, so it should be loaded. Then increment it by 3. As you can see, we have to add 3. Then store the value back in memory. Then we have to back into that the memory address of this value in the address space. So we have load, increment, and store. So address translation, let's see the assembly code. This is the assembly code. As you can see, we have, this is a pointer, stack pointer, 128, 132, 135. This is the addresses of the codes. So what it does is, the first one is EBX, these are registers. So what it's, the first code, what it says is load EBX into EAX. So the register from EBX, okay, whatever value, load it into the register EAX. This is the first line of code. The second line of code, it says add 3 to EAX. So once the data is here, so the second line of code, what it says is add 3 into the value which is registered in the register EAX. Then the third line of code, it says move EAX, okay, back to memory. Okay, back to where? EBX, because EBX is the first, the data was the pointer that the data was registered, the registered value EBX. So presume that the address of X has been placed in EBX, or let's assume in the EBX register. Okay, then load the value at that address into EAX register, then add 3 to EAX register, then store the value EAX back to the memory where EBX. Okay, that is what it does. I hope you understand. So as you can see here, address translation. So this is the virtual memory, 16 kilobyte, and the 3 codes, the program codes are here. Move 100 EBX to EAX, then add 3 to EAX, then move EAX to EBX will be here. So what it does is fetch instruction at address 128. This is the first line of instruction. So 128, what it does will be, it will fetch the value of the EBX into EAX. Then the second one, execute this instruction, load from address 15 kilobyte, because the EBX register is here in the stack, because it is a variable, so 3000 is here, so it will load it into EAX. Now the value of EAX is 3000. Then fetch instruction at address 132, add 3 to EAX, so the value of here is 3000. Now add 3 to EAX will be executed. So execute this instruction. Here there is no memory, it will add 3000 plus 3, 3003. Then fetch the instruction at address 135, move EAX to EBX. So move the value of EAX to the register to EBX. So what it does will be execute this instruction, store to address 15 kilobytes. So instead of 3000 this one, now the value will be 3003. So in the nutshell, that's what this code does. So relocation address space. The process view of virtual address space is from 0 to 16 kilobyte. As you can see, this is a virtual address, and the process assumes all the stack, the heap, the code, all this 16 kilobyte is what the process, the address space is from 0 to 16 kilobyte. It might be the case that this maps exactly to physical memory, if that was the case, if the physical memory and the virtual memory was the same, but that is not the case, because the operating system will take the space from 0 to some memory size. It will take the operating system, so it cannot be the case. You cannot one-to-one, it cannot be one-to-one relationship. Okay, so the operating system wants to place the process somewhere else in the physical memory, not at address 0, because at address 0 in the physical memory is our operating system. So you cannot take 0 from virtual memory and map it into physical memory. The address space starts at address 0. Always the address space starts at 0, but not in physical memory case. So a single reallocation process looks like this. As you can see, we have the address space, we have the physical address. The address space which starts from 0 kilobyte and 16 kilobyte will be, this is the size. But in the when relocation, the operating system, as you can see, the operating system will take 16 kilobyte already in the upper part of the memory, the physical memory. So this is how it took 32 kilobyte plus 12, it is 48. So this is a reallocation process. So the operating system, with the help of the hardware, so they assign it here. Okay, so this is the physical memory allocation. We have 64 kilobyte, but the physical memory is translated into the address space, translated into the virtual memory into physical memory. Dynamic reallocation hardware-based register uses base and bound register. This is very important point. What it means, as you can see, we have the address space here. The address space always will have a bound register. So this is a bound register. And the base register, which will be assigned by the operating system in the physical memory, we call it base register. So in this scenario, the base register is 32 kilobyte. So in the translation process, 32 kilobyte plus 16, the bound register will give us 48 kilobytes. So the translation is always the base and the bound. The bound is always in the address space, and the base register is found in the physical state, in the physical memory. And this base register will be assigned by the operating system. So dynamic hardware-based reallocation, what it does is the program is written and compiled as if it is loaded at address 0. Always it is address 0. It is the assumption. But what happens when a program starts running, the operating system decides where in the physical memory a process should be loaded. So once the program starts running, the operating system decides where this program will reside in the physical memory. So what happens is, set the base register a value. Physical address always is equal to the virtual address plus the base. So as you can see, we have the bound register. So always whatever address you have here, so the physical address will be always base register plus the virtual address. So once you know the virtual address, you have to add with the base register, then you will get the physical address where the whole code and everything reside in the system. Every virtual address must not be greater than the bound and negative. Okay, so the virtual address always should be less than bound, because as you can see here, the bound is 16 kilobytes. So you cannot have any address more than 16 kilobyte, the bound register. Again, it's not allowed to make negative because 0 is here. So it should be from the virtual memory should be from 0 kilobyte to 16 kilobyte. That is the idea. So reallocation and address translation, as you can see here, for example, in our example 128, okay, move EBX to AX. This is a code in stack pointer 128. So fetch instruction at address 128. Okay, 128. What does this mean? So physical address is equal to 128 plus 32 kilobytes of the base. So because if you see here, the base address is 32 kilobytes. So 32 kilobytes, okay, plus that is the base, plus the virtual address is 128. So when you add up, you will find 32,896 bit. Okay, byte will be the address of this instruction. Again, execute this, load from address 15 kilobyte here. So the virtual address is 15 kilobyte, the base is 32 kilobyte, so 47 kilobyte will be the exact physical. 47 kilobyte here is the exact physical memory of this code. So in this way, we can translate the virtual memory into two ways of bound registers. two ways of, we can say, for example, a bound, the size of address space can be, we can say the bound is 16 kilobyte here. We can say like that. The other way of expressing the bound register is, we can say physical address of the end of address space. So the bound can be 48 kilobyte as well, because 32 plus 16 is 48. So we can say the bound value can be 16 kilobyte, or in physical memory it could be 48 kilobyte. These are the two. So let's see an example. Give a process this address space size 4 kilobyte for virtual memory, and load a physical address 16 kilobyte. This is the base address, okay? Let's say in the physical memory we have 16 kilobyte assigned as base memory. So let's translate. For example, if the virtual address is 0, the physical address will be 16, because 16 plus 0 is 16. If it is 1 kilobyte, then 1 kilobyte in the virtual means the base address is 16 plus 1 is 17. If it is 3000 byte, then the base address is 16 kilobytes plus 3000, we get 19,384 byte, okay, or 19 kilobyte. If it is 4,400 byte, it is fault, out of bound, because the address space is 4 kilobyte. So as we have seen here, the bound cannot be greater than the bound register 16. So in our case here, the bound is 4 kilobytes, so it cannot be 4.4. That's why we get 4 out of bound. So summary of hardware support needed for dynamic reallocation. So the processor mode, kernel mode, and user mode determined through a processor status word. This is a control register. And memory management unit, as we have seen, base register and bound register. Changing the base and bounds register should be allowed only in kernel mode, because we cannot simply change the base and the bound registers when scheduler switch. Okay, when scheduler switch processes, so it should be that way. Processor should be able to generate exception during illegal memory access. And as you can see, we have hardware requirements and we have the node here. So privileged mode needed to prevent user mode process from executing privileged operations. Base and bound registers need pair of register for CPU to support address translation and bound check. So we have always one pair of base and bound in our CPU. And ability to translate virtual address and check it within bound. This one is circuit key to do translation and check limits. In this case, quite simple. Privilege instructions to update base and bound. Operating system must be able to see these values before letting a user program to run. Privilege instruction to register exception handlers. Operating system must be able to tell hardware what code to run if exception occurs, and ability to raise exceptions when process try to access privilege instructions or out of bound memory. So other issues, let's see, operating system issues that the operating system must address for dynamic reallocation. The operating system must take action to implement base and bound approach, as we have seen now. So 4 critical junctions are there. When a process starts running in the virtual memory, in the address space, so the operating system finding the space for address space in the physical memory, maintain a free list. This is one. When a process is terminated, reallocating the memory from use by other processes. This is another. When the context switch occurs, saving and storing the base and bound register pair for each process, since we only have one pair per core. And when a process is blocked, it can easily be moved to a different location. At boot time, the operating system must set exception handler using privileged instructions. So let's see operating system issues as we have discussed. Let's see what does it mean. When a process starts running, the operating system must find a room for a new address space. So free list means this is the free list, for example, a list of the range of the physical memory which are not in use. As you can see here, from 32 kilobyte to 48 kilobyte it is in use, but 16 kilobyte and 48 kilobyte are free. So the operating system have a free list showing where is the free location of in the physical memory. When a process is terminated, the operating system must put the memory back on the free list. As you can see, process A was running and this one was not in use. We have the operating system. So what it does when process A stops, then the free list will back the memory again and it will put it in the free list like this. Then when the context switch occurs, the operating system must save and restore the base and bound pair. So in process structure or process control blocks, PCB. So let's see, here process A is currently running. So process B is going to run. So what it does is the base and the bound register, as you can see in the process control block, base is 32 kilobyte and bound is 48 kilobyte, then it will be registered. Okay, then process B will continue from 48 kilobyte to 64 kilobyte. So all the data for process A progress will be registered in the PCB process control blocks. The base and bound values will be registered. So in the nutshell, that was chapter 15. So we discussed the issues, and as you can see, when it is terminated, the free lists, and all when the program start, terminate and switch, all what it happens, and summary of the hardware support, what is base register, bound register, everything was discussed. And we see also an example how to translate from virtual address to physical address, and what is virtual address and physical address we have discussed, and two ways of bound register. We can use the virtual address space of the process, or we can use the physical address, and both of the same way to express. And reallocation in address translation, as we have seen, the physical address is always the virtual address plus the base. The base is assigned in the physical memory by the operating system, and the virtual address, the bound should not be. So as you can see, the virtual address cannot be zero, negative, or cannot be greater than the bound. And dynamic reallocation, we have seen how the bound and the base works. A single reallocation address space, and address translation, how the programming, how book works, and the load, incrementing, store, and address translation, virtual address to physical address. Hardware needs the operating system need the hardware support. And in the nutshell, that was the address translation chapter 15. I hope you get something from this video. I encourage you to read the book and to download all the codes and the homeworks and practice and get better. Thank you so much. I will come up with another chapter 16 next video. For now, I really appreciate for your time. Okay, thank you. Bye bye.